And this session would be focusing upon the source apportionment and emission inventory studies and how they can help us in formulating better air quality action plans. For this session, we have Ms. Emil Varghese, who will be chairing this session. And as panelists, we have with us Dr. Shweta Yadav, who's an assistant professor at the Department of Environmental Sciences at the Central University of Jammu. Mr. Anirban Banerjee, who's a senior associate at the Policy Development and Assessment Group at Air Quality Sector in CSTEP. Dr. Albert Presto, who's a research professor at Carnegie Mellon University. And Professor Deepika Bhattu, who's an associate professor at IIT Jodhpur. I would request the panelists and the session chair to please take their seats at the dais. Ms. Emil Varghese is a senior analyst at CSTEP, and she's a part of the Atmospheric Composition Observation Group and heads the INDISET Center project at Bengaluru, where they manage air quality monitoring, where they've set up an air quality monitoring station and evaluate air sensors from various manufacturers. She's also pursued her PhD in environmental engineering from IIT Madras. I would now invite her to please take forward the session. Thank you.
Yeah, hi all. So in the last session, we were talking about the need for having a healthy air for everyone and everywhere. And to develop a framework for effective air quality management plans, an understanding about the air quality is essential. That is, how much is the pollution, where is the pollution, when is the pollution, or what are the contributions of the various sources to the air pollution problem. So in this session, we'll be discussing about the various pollution sources, the amount they contribute to the air pollution problem, and what is the emission reduction potential of the possible mitigation measures. So in this session, we'll be having 4 speakers, and 15 minutes will be allotted for each speaker. So by the time of 12 minutes, we'll be having a bell ring, so that in the next 3 minutes, we'll have to be concluding that. And then this will be followed from one question from the audience. And once all the speakers are done, we'll be moving the questions to the audience. So India has a wide variety of land use patterns, geological setting, and climate regimes. Likewise, the sources of PM are also expected to vary from different parts. So we have our first speaker, Shweta Yadav, who will be talking about the source apportionment studies across India. Dr. Shweta Yadav is a faculty in the Department of Environmental Sciences, Central University of Jammu and Kashmir. She is also adjunct faculty in the Department of Civil Engineering, IIT Madras. She was awarded with Fulbright Kalam Climate Fellowship for postdoctoral research in 2017, and she has got selected as a member of the Indian National Young Academy of Science. She is also nodal faculty from Jammu and Kashmir and working as a technical partner to Jammu and Kashmir Pollution Control Committee under the National Clean Air Program. Dr. Yadav works in the field of aerosols, air quality, and climate processes. She is a pioneer in carbonaceous aerosol research and has established the Himalayan Aerosol Research Instrumentation Facility. Her research group is interested in understanding the chemical, biological, and cloud forming and ice nucleating properties of aerosols to understand their implications on the Himalayan climate and ecosystem health. Her work on bioaerosols and ice nucleating properties of aerosols targets to find answers to the fundamental science questions on cloud formation, precipitation, initiation, and ecosystem health. I welcome Dr. Shweta Yadav.
Thank you, Emil. Good morning, everyone. Quite timely. So at the outset, I want to thank entire CSTEP team for having me here. Thank you, Subbu, especially for bringing me here to this ICAS 2024. So I was present in the last ICAS also, and I must congratulate you for having a wonderful conference back-to-back. And the expert speakers and the entire program is very enriching for even me. I have been asked to talk about source apportionment studies across India, the current status and future needs. Given 12 minutes, I am going to focus on source apportionment studies. Very quickly, I want to tell, which Emil has already told, our focus and our research group is specializing in offline chemical characterization. And in last 20 years, I have been doing a lot of chemical characterization and source apportionment studies and stuff. We are evolving in investigation of bioaerosols, developing facility to study INP, and we are serving as technical partner and working with policymakers, academicians, and local people. And we are doing mostly offline chemical characterization, and this is a small facility which has come up in Central University of Jammu. It is called Himalayan Aerosol Research Instrumentation Facility. So our university is at around 550-meter AMSL, and now I'm very happy to announce that we are coming up with this Himalayan High Altitude Atmospheric and Climate Research Station at 2250-meter AMSL. So coming to the air pollution problem, I think already much have been discussed and said, and it's really a major challenge. And coming to the source apportionment studies, so if I look back, we have been studying the chemical constituents of aerosols for quite long. But it's, I think, after National Clean Air Program that we are talking more about the source apportionment studies, and we are using this terminology more frequently. So some students are also here, so I want to clarify that I'm not touching sensors because already everybody is trained, well informed on sensors. So broadly, if we see, we have two types of source apportionment studies. First is the offline one, where we do sampling, then offline chemical analysis, and then receptor modeling, and another is the online sampling, where we are using TOF, ACSM, or AMS, and then simultaneous online analysis is done and receptor modeling is done. So basically, when we talk of offline source apportionment studies, it is very important to have a good sampling design, what we are targeting, and which size fraction is in focus, selection of air samplers, all of this is very, very important. And the major chemical classes of PM, as we know, are carbonaceous fraction, water-soluble anionic species, and major and trace elements. So what are the chemical species we are going to target is also very important. And with size fraction, of course, because as we know that in National Clean Air Program, the non-attainment cities were identified on the basis of PM10. And when we talk of health impacts, PM 2.5 is more important. So which size fraction we are targeting is again an important decision to make. And once we are having the chemical constituents, it's very important to see the dynamics and to see the other things which are there with that data, which we can get the information with the chemical markers and all. And levels of assay and air quality management is one important aspect of source apportionment studies. We can have different 3 levels broadly. One which is 24-hourly sampling, where we are going to have for the city kind of source apportionment. Level 2 is diurnal sampling, which further helps in understanding the peak sources. And third is level 3, where we are doing the real-time source apportionment with high-resolution data for fine temporal scale. So, of course, with that, the QA/QC adherence in assay studies is very, very important, like what is the ideal combination, the analysis of aerosol samples, and further to identify more complex overlapping sources, what are the isotopic ratios we are using, what is the methodology and all. So receptor modeling is the last step of source apportionment study. Again, if we are having a good number of samples, then we can go for positive matrix factorization. We can go for CMB if we are having the source profiles. So this is again a very important question which we have to decide, or a decision which we have to make when we move further. Importance of metrology has to be taken care of while designing a source apportionment study. This is a review paper in which we have discussed all this for detail. You can go through this review paper. So when we talk of this current status of source apportionment studies, so this is one diagram from the same paper. I don't think you can see the numbers, but basically I want to show from here that the major fraction, as we already know, is contributed by organics or sulfate or nitrate. So these are the chemical constituents which need to be focused in more detail. So if the source apportionment study has been conducted, these chemical constituents, if studied in detail, can help you further in understanding their impacts on climate and human health. And this is studies pertaining to each size fraction. So of course, we have dominance of PM10 studies, and very less size segregated studies have been done all over India. And when we talk of the studies pertaining to combinations of chemical species, so while reviewing the source apportionment studies, what I found is that if we are only doing the metal species, and if we are applying PMF, we are calling it a source apportionment study, right? If we are doing any constituent, but to have a complete picture, at least all three important components must be quantified. Then only you can get a complete picture of a source apportionment study. So we only found 41% studies where all three combinations were done, and others are like with specific constituent source apportionment was done. And this is again a data which is showing that most studies are from Delhi NCR, Indo-Gangetic Plains, and very less studies are from Central India and Western India. So this kind of thing is there, and I think now there are many studies from other parts of India after the inception of National Clean Air Program. And this is again the combination here. Oh, I'm sorry, I'm going back. So this is, so when we just look at the current status, the important questions are which level we are targeting for a source apportionment study, what are the target chemical species, and of course the budget constraints. Because when I sit in the national committees, I have noticed that many pollution control boards are floating tenders for source apportionment study. And then they ask you to do the source apportionment for this chemical constituent, that chemical constituent, and that time what the person can do is can only compromise on the number of samples. Right, so this is very important, that what kind of source apportionment has been done for a city planning. At that time only, if the correction is done, we are going to have a good data which can be comparable tomorrow. So most studies, as I said, are from Delhi NCR and IGP. The methodology as well as source classes vary across previous source apportionment studies from India. The unavailability of comparable data has allowed limited meta-analysis of percentage contribution of major sources from offline studies. So I think this is one of the areas where we all can work together and to have some kind of data which is comparable, so that meta-analysis is available tomorrow. And the future needs, if I say, of course, the plan of essay studies should be very clear. And as the previous speaker, Dr. Balakrishnan, was talking about the scope of National Clean Air Program, and it was mentioned that any National Clean Air Program cannot be there if household air pollution is not there or the rural areas are not there. So what I personally think for the future is there are three approaches where we can increase the scope of National Clean Air Program. One is going to the ministry, and ministry announces these are the changes at national level. Second is that the senior people already are here, or the philanthropies can approach the people who are already doing the source apportionment studies in different parts of the country. And they are already having a very good number of samples. Like our group has done source apportionment for Jammu, so we are having good 1,000 number of samples on quartz filter papers. So we can have further studies with those available filter papers. And second thing is the capacity building has also taken place through the National Clean Air Program. So if you want to conduct some kind of other studies, then these people or these facilities can be used to have some subgroup, and this can be very, very beneficial for future. So the National Clean Air Program has at least done the capacity building, and of course there is no limit of expanding the future scope, but we must acknowledge and appreciate that yes, the society is more aware now, and we are more doing the work towards the future needs. So the broadly uniform guidelines should be followed for the source apportionment studies, and keeping in mind the implications of PM 2.5 on human health and air quality, it will be appropriate to first complete essay of fine fraction on priority basis. Again, there's a conflict because the Pollution Control Board says that do the source apportionment for PM10. So this has to be resolved somehow. And combination of the traditional offline filter-based techniques and highly time-resolved online assay techniques should be used. This is going to be very, very beneficial. So simultaneous measurements with collocated instruments will surely help, because to understand the chemistry of aerosols and the implications all over, this can be one of the solutions. So with this, I close, and these are some of the review papers from our group, which you can further go through to have more details on this. Thank you, CSTEP, for having me here once again. Thank you, one and all.
Thank you, Dr. Shweta. Now we can take one question from the audience. Please introduce yourself.
Yeah. Hi everyone. I am Manu Sharma. I am a PhD student in IIT Tirupati. Very good presentation, ma'am. Just a small question or like your thoughts and comments about the requirement of inbuilt source profiles that we at present don't have much in our country, but still, I mean, we are using different receptor models, but the main, or I would say the primary criteria is that we should have indigenous source profile to get more representative of the sources that we have. So, I mean, what are your thoughts about it? That's it. Thank you.
See, as I said, the receptor model which we are using is totally dependent on whether the source profile is available or not. So one mistake which has been done by some groups is that we use source profiles which are there for US or Europe. So we have to have our indigenous source profiles, of course. But another solution can be that you can go for positive matrix factorization, because if you are having good number of samples, then source profile is not the preliminary requirement for that. So of course, there is a requirement of having indigenous source profiles, and source apportionment using CMB and all must be done only with the indigenous source profiles only. And I think many groups have already started working on this direction, and in future, I think more indulgence will be required. Yeah. Thank you.
Yeah, once again, thank you. An emission inventory is an effective tool for identifying the sources of pollution and quantitatively expressing the pollution load in a defined area at a particular time. We have our next speaker, Anirban Banerjee, who is a senior associate within the Policy Development and Assessment team, specializing in an air quality at CSTEP. With an MPA in research and over a decade of experience in the climate and air quality field, his interest lies in emission estimation, policy analysis, and the development and implementation of pathway development of policies aimed at enhancing air quality standards. I invite Anirban to speak regarding the findings of CSTEP study to understand the various air pollutants and their share in the pollution.
So, like Emil said, I'm going to present our findings for the newest study, not newest, but anyway, yesterday one of the portal was launched which has emission inventory for 76 non-attainment cities in India. So, just I'm going to go through their findings and why we did the study. So, before that, let's start with what is the research team. On the left, you have the research team, and on the right, we have the collaborators. So, we collaborated with 12 IOAs, Institute of Reputes, IITs, NITs, central universities, and the names are purely alphabetical order and not for their contribution to the study. So, yeah. The motivation was obviously NCAP, National Clean Air Program, which was started in 2019. 131 cities were selected. Out of that, 82 was non-attainment cities and 49 was million-plus cities. So, as of 14th August, almost 11,000 crores were disbursed for the air pollution mitigation measures. However, only 37% of the cities has completed emission inventory and source apportionment studies. So, when we started at 2020, somewhere peak of COVID, this project, that time this number is much lesser. To be frank, it's less than 10% of the cities has the information to at least look at what are the dominant sources and what are the mitigation measures, how it will reduce the emissions. So, we thought it's very important to understand what's the source contribution, and because it's city specific, we went into emission inventories. So, what is emission inventory? It is to understand where is the pollution, how much is the pollution, and why that pollution means, what are the activities which is contributing to this pollution. So, emission inventory is nothing but is a comprehensive listing of sources of air pollution, and basically it's a emission or any whatever pollution is coming out of the direct sources, we are not looking into the concentration part, which is obviously there are physical and chemical changes happens when a emission comes or pollution comes out of the sources. So how why emission inventory is required? The last point is most important here, the distribution and the control measures. Distribution means how the emissions are distributed over a geographic area and what are the control measures you have to take it to reduce that. So for the 76 cities, we looked into 17 states and UTs, means 17 states and 1 UT, 16 states and 1 UT to be frank. So not all the cities were considered because already some of the institutes are working on those other cities. The left side figure shows that what are the cities we have, what are the number of cities each state we have taken up, and how on the right side we have what are the secondary data we have collected, what are the government bodies we approach for the data, and the type of surveys we have conducted. So if you look at fuel station survey, if I purely go by the number, we have collected more than 130,000 data points to consider what is the vehicle spread and the vintage, because vintage plays a very crucial role in the total emissions what is emitting. So before going into result, let's look at the assumptions. Because it's an emission inventory, the data is very much important, and India is a data starved state. And very few Indian states has the granular activity level data we require for developing an emission inventory. So if you look at transportation, one of the best source of data is Vahan database. As of today, we have almost 20 years list of registration data available. But when we started, when we estimated, it was only 10 years worth of data was available. But emissions doesn't come from only 10 years worth of registered vehicle or vehicle plying on the street. They're the more older vehicle. So there is these limitations are there for anybody who is preparing an emission inventory for the cities, and the assumptions might change, but ultimately what we are looking at, and there might be questions, there might be better assumptions. We try to take assumptions what is most suitable for us, and we can, if any further questions are there, I can try to resolve why we have taken these assumptions. So let's look at the one of the cities data for Karnataka. This is the output you will see in our portal, and if you go through the report, you'll have much more details how we came into it, what are the costs required, because as Professor Kalpana already mentioned, ultimately it boils down to economics. How much money the states or the government needs to put. To be precise, we only calculated government capex fund, but which is not mentioned here. But what you are seeing here is the information you will get when you look into our portal. So we have, sorry. Okay. Sorry. So this is the Davangere city. If you look at, this is the Davangere city. If you look at, and sorry, yes, some problem. Yeah. This is the Davangere city, and the outside the grids, what you are seeing is a bigger area beyond city area. Why it is required is because there are dispersed sources as well as industrial body, which is industrial development like pharmaceutical and somehow, sorry. So if you look at the western side, northwestern side of the this graph, and this is spatially located. This is, every grid represent 1 square kilometer, and the northwestern side you have there is a garment manufacturing industries, there are pharmaceutical, and if you look at the just north of the city boundary, you will see there is a darker color shade. I don't know if the numbers are visible, but this is because of the puffed rice industry. There is almost 950 puffed rice industries there. So, and on the right side, the pie, what you are looking at is that it's basically the city share, what are the sources, and many of my colleagues previously also mentioned that domestic is one of the major sources. So, all the 76 cities have this kind of information available, and also we projected the emissions, looked into the control measures, prescribed control measures from the government. Also we considered some of our control measures, but mostly we saw that by 2030 we'll be able to reduce the emissions with certain control measures by 35%. So if we purely going into local emission control, we will not be achieving 40%. I understand NCAP is for concentration and not emissions, but we will not be able to even reduce emissions by 40% by 2030 for 2026. And that's the baseline, from the baseline of 2019 and not 2017, which is prescribed in NCAP. So there are some of the major control measures which you can see, which is cost effective. Why cost effective? India is still developing, it's not developed. We don't have unlimited money. We have to spend money where it counts. So it's better to be more cost effective in terms of emission reduction potential. So this is our recommendations for best three policies. Now look at city level, what is how it looks. We divided into 4 zones, western, north, east and the southern zone. And if you look, the darker the color, the more PM 2.5 values are there. And again, this is only for the city. If we purely go by the bigger region, it may completely look different, because most of the industries are normally just outside the city area or couple of kilometers away. So, for example, if you look into the Chennai area, so this is Chennai, and that is showing a little bit less darker color because the thermal power plants are just outside the city boundary, just outside. So even if we start looking into the bigger Chennai region, then it may look completely different. So the population of these cities, 76 cities, varied from 2,000 to 83 lakhs. And similarly, the emission varies from 35 tons per year, which is Paonta Sahib in Himachal Pradesh, to 14,000, almost 14,000 and a half, 14.5 thousand kilotons for Kalinganagar. If anybody knows about Kalinganagar, if you look at the satellite view, you will see the Kalinganagar is nothing but a SAZ in Odisha, ACZ. So if you look at, they have at least 3 or 4 integrated steel plant. And the population there is actually less. The same way, if you look at Birnihart and northeast, the same way, that's why the population is very low, but it's an industrial hub. So, however, CPCB considered that to be a city, so we have also captured the information here. Now, like I said, because this city has variable land use, so the emissions does not scale with the city population. So if you look at the left side figure, it's basically the marker shows the population of the city, and at the right there are 3 dots which is more visible on the right side, and you will see that from NOx emission and PM 2.5 graphs, you'll see that Korba, Tuticorin and Kalinganagar at the almost on the right completely. For the PM 2.5, they are quite huge. And why? Now the question is, why the NOx emission is also not proportional? Why Kalinganagar has less NOx, whereas Korba and almost, if you look at Tuticorin is on a straight line, and Korba and Kalinganagar has completely opposite direction. So because of the time, I'll go to the next slide, which is dominant sources in each city can be completely different. If it, like I said before, Korba has more NOx, whereas Kalinganagar has less NOx in terms of with respond to PM 2.5. So we can talk about Korba has more probably both industry and the transportation plays a major role there, whereas in the Kalinganagar, SOx, because of the industries, coal users in the integrated steel plant, it's the SOx emissions are more. Now the most important thing, the cost part. If you look at, we took two cities for each zones, and if you look, the color indicates the sectors, what can be reduced, how much can be reduced, and the gray part is the cost. So we have Chennai, which is can be reduced more on the transportation because of electrification, and the cost is also high. It's close to 2,700 crores or something. Same you will see in the Ahmedabad. Ahmedabad, by the way, it's a mixed development, so there is also some industries. So that's what the costing is more. And industry, for some of the cities, you see the cost is less, but the reduction is more because we didn't calculate the cost from the industries. And because of that, it's a government needs to pay very less amount to get more benefit. The summary is basically, again, varies from 35 tons to 14,500 tons based on the city. That largest emission sources for transportation, industries and domestic. There are different regions because of the city choices are different dominant sources, and the cost is more on the tier 1 cities because of the electrification of transportation requires a lot of investment, and funding requirement you can read it out because more time is not there. So let's end it here. Thank you.
Yeah, thank you, Anirban. Now we can take up one question from the audience. Yeah, in the back.
Thank you, sir, for the nice presentation. I am Alok from IIT Gandhinagar. So the question is, how do your collaborators decide where to put the instrument? Like Chennai might be putting it at a traffic signal, and another collaborator of yours might be putting at a residential, near the residential setting. So comparing results can be maybe troublesome.
I understand. So here the collaborators help us get the data in activity data from the government, and they helped us towards the survey, because sitting in Bangalore it was, and because COVID was running, we needed help, and we approached NKM, National Knowledge Network, that, and Professor Tripathi, who was gracious enough to give us the contacts and help us contact with the other institutes who helped us for getting the data. So data in the sense, how much, what is the, say for example, Telangana and Andhra Pradesh didn't have Vahan database, and still now, or didn't have Vahan database is the wrong choice of word, they didn't upload the data into Vahan database. So we didn't have any access to the number of registration. So we approached the IORs, our collaborators, they reached out to RTO, got the data and shared with us.
Okay, sir. And
there is no instruments involved.
Sorry
here.
to interrupt, like we'll have the question discussed in the later step. Yeah. Thank you, Anirban.
Thank you.
Yeah, moving to the next speaker, Dr. Albert Presto. Dr. Albert Presto is a research professor in the Department of Mechanical Engineering at Carnegie Mellon University and is the director of the Center for Atmospheric Particle Studies. Presto's research focuses on pollutant emissions from energy extraction and consumption and the subsequent atmospheric transformations that these emissions undergo. Energy production and consumption is a major source of pollutants and greenhouse gases in the atmosphere. Particulate matter from mobile sources is largely the result of incomplete or inefficient combustion in the form of organic aerosols and carbon soot. In addition to the direct emissions of pollutants, dilute exhaust undergoes oxidation in the atmosphere. This oxidation chemistry can lead to the production of secondary pollutants such as ozone and secondary particulate matter. PRESTO investigates the contributions of primary and secondary pollution with ambient measurements, laboratory experiments, source testing of pollution sources, and atmospheric models. This multi-pronged and multidisciplinary approach allows for a holistic view of pollutant emissions and transformations in the atmosphere. In addition to having environmental impacts, these pollutants, particularly ozone and particulate matter, adversely impact human health. PRESTO collaborates with medical professionals to develop detailed studies of pollutant exposure on a neighborhood-by-neighborhood basis and to better understand the relationships between pollutant emissions and adverse health effects such as childhood asthma. Black carbon aerosol particles, which results from the incomplete combustion of fossil fuels, wood, and other biomass, constitute up to 10 to 15% of PM 2.5. Dr. Albert Presto will be talking today on the low-cost ambient black carbon measurements. I welcome Dr.
All right, so I'm going to talk about some work that we've been doing this is not necessarily a low-cost sensor. We talked a lot about sensors the last few days, but this is a low-cost way to sort of gain additional information from existing measurements. Oh, there we go. All right, so 2 points that I would like you to remember from my 12 minutes up here. One is that reducing black carbon emissions and concentrations has positive impacts on both climate and human health. And we've already heard a bunch about black carbon this morning. And I'm going to show you how we're using existing measurements to quantify black carbon in places worldwide, and especially in places where there isn't existing data. Okay, so black carbon is emitted anytime you combust a fuel. And so those combustion sources can be fossil fuel-fired vehicles. It can be when you're burning wood, either to clear a field or in the home for cooking. And it can also be emitted from combustion associated with industrial sources. So I'm showing a fossil fuel-fired source on the upper right, but then also sources like brick kilns in the bottom right. Black carbon is a component of particulate matter, and we heard a lot this morning already about how particulate matter exposure is harmful to human health. In some of the places that I'm going to show you data from, black carbon is a large fraction of the total particulate matter loading, and so reducing those emissions would reduce PM and improve health. And then, of course, black carbon is also a climate forcer, and this is really well explained in the case for action on black carbon. That's a really excellent document that CSTEP put together. One of those climate impacts is black carbon can deposit on snow or on glaciers. Now your white surface is black, it absorbs more sunlight and melts faster. What we've been doing over the last few years, and we're working to expand, and now my slides are going on their own, is to take advantage of existing PM 2.5 measurements around the world. One of those sources of measurements is that at US embassies worldwide, sorry, now my slides are auto-advancing, is that there are PM 2.5 measurements at US embassies around the world. A lot of those use what are called beta attenuation monitors. Sort of the key aspect of BAMs or beta attenuation monitors that we take advantage of is that it collects a spot every hour. So the BAM has this filter tape, that's what's shown on the right-hand side of in the photo. And each spot is a particle deposit that is collected over 1 hour. What we do is we essentially look at how gray those spots are. So you can see maybe a little bit that those spots have different levels of grayness. That corresponds to different levels of black carbon in those individual hours, and we're going to take advantage of that data. So the BAM itself is an expensive instrument, but the value we're adding is a really low marginal cost. I'm going to note that, so the colors on the map show a distribution of where we've already done some data analysis, where we're expanding to, and where we would hopefully like to expand. So as of Monday, I have a new project starting on this that is funded by the NSF, and so we are very open to collaborate. So, and we can operate in a mode where some of these embassies send us their tapes and we do the analysis, but we also have collaborators where we have, thank you, where they collect their own tapes and we just have shared with them the code and the methods and they do their own analysis. The way that our method works is that we photograph those individual spots. So each spot is a different level of how gray or not gray it is. We photograph that with a cell phone camera. So this is a very low cost method. You just need to basically print this piece of paper that has what's called our color reference. And then we analyze the photo. So photographs have 3 color channels, red, green, and blue. And what we do is we look at the red channel and essentially compare how gray is the spot compared to how gray are these boxes on our reference sheet. And so we calibrated this method. My student, Abhishek Anand, who just finished his PhD, collected a bunch of filter samples and photographed them. And what we saw is that we have this expected relationship between the black carbon loading in each spot and this red scale value from the photograph. Before we applied this method to filters collected in other parts of the world, we wanted to make sure that our calibration was robust and it wasn't just sort of specific to our location in North America. And so one of the comparisons that we did was that we had access to a BAM filter in Addis Ababa, Ethiopia, that was co-located with an ethylometer. And so we had hourly data from our method, hourly data from this ethylometer, and that's the comparison I'm showing on the right, and we have really good agreement. So this is a summary of most of the locations where we have now analyzed data from various BAM tapes. So this is black carbon concentration, or the distribution of black carbon concentrations at a bunch of different locations. And we see a lot of variability. So I want to point out first, Pittsburgh, which is where our campus is in the US, is on the far right. We have relatively low concentrations there. And then a variety of other locations, mostly in Africa and one in Asia. In general, those concentrations are much higher than what we see in the US. So some of these locations, we have 5 microgram per cubic meter of black carbon. That's approximately 10 times higher than what we measure at our location in Pittsburgh. And then we see a lot of variability. We see variability between these sites. We see variability among different seasons. One of the real big strengths of our method is that because we have these hourly deposits, we can understand how concentrations change over time, both within a day and across, for example, a season. And so I'm going to show you several examples from Abhishek's paper that just came out over the summer, and I'm going to use Accra, Ghana as one of the examples. And so what I'm showing here is a time series of one tape in the BAM. So the BAM, you load this tape, it lasts for about 2 months. This is one full tape from the BAM at the US Embassy in Accra. The black line is the black carbon concentration that we get, again, hourly. And the blue line is what the PM 2.5 that the BAM measures, and that data is publicly available. So we can see a few features here. One is that black carbon and PM 2.5 go up and down on a sort of daily pattern, and on most days, those two quantities are pretty well correlated, and that is because of similar activities are generating local emissions of PM 2.5 and black carbon. The atmosphere is sort of diluting them in the same way, and so we get this up and down pattern. There's this period here where they diverge. And so PM 2.5 gets very high, and black carbon is pretty similar to what it was the rest of the time. This is during the Harmattan, so those who have been here all week have heard about Harmattan several times. These are big dust storms that blow in from the Sahara and drive up PM 2.5, but there's no combustion that's associated with that, so the black carbon doesn't increase. Because we have hourly data, we can generate these diurnal patterns, which are the sort of estimate of a typical day. So now this is the black carbon concentration versus typical, averaged over hours of the day. And I'm showing, again, this is Accra. So the weekdays are in black, Saturdays in red, and Sundays in blue. And so we see on all days, there's a peak in the morning at about 8 a.m. That's from the morning rush hour. So this is people going to work and starting their day. Concentrations drop in the afternoon. That's from dilution, from convection in the atmosphere. We also see that concentrations are a little bit higher, and that morning rush hour peak is stronger on weekdays than on weekends. And that's consistent with the fact that in Accra, less folks work on the weekend than on weekdays. In places where, for example, Saturday is a work day, Saturday looks like the other weekdays and Sunday is different. The last feature we see here is that there is this peak in the middle of the night, 2, 3, 4 in the morning, and it shows up on weekdays, it shows up on weekends. We're not exactly sure what that source is. It's some sort of local combustion. It might be generators from intermittent power outages. It might be people burning trash. But it's something that shows up in multiple locations. So this is the same sort of diurnal for Kampala, and we see the same sort of features, right? We see the big peak from the morning rush hour, but again, we see at about 2 in the morning this peak that arrives. And again, that's from local combustion. We're not sure exactly of the source at this point. We can use this ground-based data to evaluate the performance of various chemical transport models. So this is showing, this is for the GEOS-CF model. First for PM 2.5, again for Accra. When we compare the model to the ground measurements, there's good agreement. The model isn't perfect, but it clearly has skill. You know, the model's under predicting the actual concentrations a little bit, by about 20%. When we do the same comparison for black carbon, the model is severely under predicting. And this has happened in every city that we have looked so far. The model underpredicts. In Accra, it's underpredicting by about a factor of 5. Right? So this suggests that the model is missing a bunch of black carbon emissions. One of the next steps that we want to take as we grow this project, we want to grow it in terms of the number of sites, but we also want to grow the sort of value that we gain out of this analysis. And one is to do some source apportionment with the black carbon. And what we hope to be able to do this optically. We have some hopeful evidence that this should work. So when you look at black carbon emissions or light absorbing particles emitted from a fossil fuel vehicle, for example, it is purely black material. So it acts like a black body, it absorbs light like a black body. When you get black carbon emissions from wood burning, there's this whole bunch of material that is co-emitted that also absorbs light, and we would call that material brown. Right? So that's why there's the black circle on the right and the sort of the black circle with the brown ring on the outside on the left. And so what we're trying to do, and this is based on a method that's embedded in sort of higher cost instruments, is to look at the relative amount of light reflected in our red channel of our photos and our blue channel. And so this is just showing some proof of concept that we've done over the summer, comparing that ratio for filter samples that are purely loaded with wood smoke versus samples that are purely loaded with fossil fuel black carbon. And so you can see there's decent separation. If I was to do a statistical test, these would be different distributions. And so what we would like to do, what we're trying to do, is to develop an algorithm that allows us to use this ratio to say whether the black carbon is more dominated by fossil fuel or more dominated by wood smoke. So, right, so that we're able to get more value out of these data. Another thing we're trying to do and that we're working on developing is that so far all of the analysis I've described are non-destructive. We take these photos, we don't, it doesn't destroy the filters. Then what we're going to do is we're going to take the individual spots and destroy them somehow. This is an example where we're dissolving the filter spots into a solvent and then re-aerosolizing that mixture and measuring it with a mass spectrometer and trying to get a sense of the full composition of the aerosol so that then we could do sort of a more full source apportionment in each of these locations. So I'll just wrap up by reiterating these points I made. Right? If we can reduce black carbon, we can have these positive impacts on both health and climate. And I've showed you how we're using these existing measurements to analyze for black carbon. And again, we are very open to sort of expanding this in either ways where folks send us tapes or where we export the method and that folks are able to do their own analyses. So thanks, everyone.
Thank you, Dr. Albert. So we can just take one question quickly.
Hi, Piyush. I'm from CSTEP. So different smartphone sensors have different sensitivity, right? So when you take a picture, there could be a difference between a Samsung phone and an iPhone, just based on sensor. So I hope you are using raw data, right, in RGB channels. So how do you account for that?
So we basically redo our calibration for everyone's phone. And so we're thinking about how we can export that. So we have a set of filters, like the set of filters we used when we built the method, we've kept. And so we redo those whenever we use different phones. So I think as we move more towards a model where we're exporting the knowledge, we will have to also send out sort of essentially calibration filters that allow people to sort of adjust for their own phone or their own lighting conditions. The lighting conditions matter as well.
The elevated air pollution levels have adverse effects on human health, regional ecosystem, crop yields, and local climate. And a well-known metric which is used for assessing the acute health effects of PM 2.5 is its oxidative potential. So now we have our next speaker, Dr. Deepika Bhattu, who will be talking about the important sources of PM 2.5 and their oxidative potential in northern India. Dr. Deepika Bhattu is an associate professor at the Department of Civil and Infrastructure Engineering at Indian Institute of Technology, Jodhpur. Dr. Bhattu obtained her PhD in environmental engineering from the Indian Institute of Technology, Kanpur in 2016. Prior to IIT Jodhpur, she worked as a postdoctoral fellow at Laboratory of Atmospheric Chemistry, Paul Scherrer Institute, Switzerland. Dr. Bhattu's research activities focus on physical and chemical characterization of atmospheric aerosols. Her group characterizes emission sources through laboratory and field experiments using various state-of-the-art and advanced analytical techniques essential to understand their origin, fate, and environmental and health impacts. The group performs offline and online measurements of gas and particles to identify their sources and investigate long-term changes in emissions and effectiveness of regulatory measures. To complement receptor-based modeling for source identification, the group also works on development of city-level emission inventory and performs dispersion modeling to understand the spatial ground-level concentration in a specified region. Over to you, Dr. Deepika.
Okay, thank you, Emil, and good morning, everyone, and thank you, CSTEP, for having me here. So the title of my talk, you can see, it's Local Incomplete Combustion Emissions Defining the PM 2.5 Oxidative Potential in Northern India. So basically, this is a take-home message which I have put as a title, but through my slides, I will walk you through the journey, how we have reached to this conclusion. Before we start, I would like to give some introduction about what is actually oxidative potential and how do we measure it and how we can relate it to the sources. So first, as we all know, that the poor air quality associated with the high levels of PM particulate matter is one of the fifth greatest health risk that has been identified. And PM oxidative potential is basically a measurement of oxidative stress in the body and what it creates the human health impacts. And rather than measuring the PM mass as the relevant health metric, it has been suggested that the oxidative potential should be used as the relevant metric. So till date, most of the studies, what they do is that they relate the PM 2.5 or PM 10 mass with the number of the admissions to the hospitals or the total exposure study or the total exposure or different kind of diseases what are happening in the country or in a region. But, and sometimes they often go in depth till the constituents of the PM. But they are not able to identify like which are the sources which are really important from the health point of view, because all sources might not be toxic. For example, I would say that dust is not equally toxic as the black carbon. For this, I would like to also thank the previous speakers who have set up the platform so that I can take it forward. Now to lastly say that to prevent the million of premature deaths and to prevent the years of life lost, the targeting the health relevant PM sources is very, very important. So to show this, we conducted a study. So it was a collaborative study. I would show at the end all the collaborators and all. So the objectives of this study was to first identify the PM 2.5 sources in the region, in the IGP region, and to identify, to measure the OP in this trans and upper IGP region, and determine that what are the different sources that are the main mainly dominating in that region. And as we know that from the graph you can see that we had almost 5 sites spanning over the northern part of the India. So one was in Haryana, Hisar, and 3 of the sites were in Delhi, IIT Delhi, and Manav Rachna University, and IITM Delhi. And the downwind site was IIT Kanpur. So we wanted to know that every year we see this debate of, blame game that happens, that Delhi is polluted by the upper regions, Punjab or Haryana. We wanted to answer that question. That was the main focus of this study. And that's why these sites were selected. And further, we wanted to not just find out the chemical constituents which are regularly done in the source apportionment studies, but we wanted to dive deep into the molecular level so that we understand that the sources which are emitting the emissions, are there some processing also happening? We know that the processing also happens in the atmospheric level. So there can be secondaries formed, and these secondaries can form up to 80% of the total PM mass. So it is very important to identify that from where these secondaries are coming from. That's why the molecular level composition was very important to identify. And then finally, to measure the magnitude of the PM2.5 oxidative potential, we used 3 different assays, which tells us about the oxidative stress created by the PM particles. And this oxidative stress can be created either in the body or outside the body. Like either they are present as the species which are bound to the particulate matter, and that is like outside the body, and also they can generate the oxidative species creating the oxidative stress inside the body. So we wanted to find out what are the drivers of these health impacts, oxidative potential basically. So here we can see, so the first line I would like to say here is that we did not only stopped comparing the different sites in India, but we also compared with the other regions, like some of the Chinese cities and European cities, and we found that the concentrations were 10 times higher during the winter season, even if we combine all the sites, what we have measured in India. So that was a major point here. And if we look at so we divided the whole entire period into the warm season and the cold season. So warm from mid-March to May, and winter was from January to mid-March. So we can see the concentration here. The concentration went up to 98 micrograms in the winter, and half of it in the summer season or the warm period. And the relative contribution, you can see here, the organic aerosols contribute about 50%. 10% of it is like elemental carbon, which we can also represent as elemental carbon. And then there are some inorganics, which contribute up to 30%. But we see that the composition is changing from winter to summer. Now, on the right-hand side, I would like to show the PM2.5 constituents. Although you will see that in this bar chart, we have put all the concentrations across all the sites. You will see that the concentrations are similar. But if we look at the constituents, they are varying too much. And that was the indicative that there might be some local sources present, and also some formation processes, like the processing of the primary aerosols that is happening. That is also happening at the local level and not getting transported from the other sites. So that was an indication. Further, we also, since organic aerosols and elemental carbon made up like 70% of the total mass, we wanted to look into the origin of these aerosols. So from where this elemental carbon and organic aerosols are coming from, they are fossil or non-fossil. So that was done using the carbon-14 radiocarbon analysis. So we can define from that whether it is coming from vehicular emissions or it is coming from which comes under fossil, and from the non-fossil sources like biomass burning or wood combustion. So what we found interestingly was this elemental carbon during the both warm and the cold period, it was coming from the non-fossil sources, fossil sources, which was vehicular emissions. And organic aerosols in both the seasons, you see they are coming from, mostly from 60% of it is coming from the non-fossil sources. So there is combustion activities which are contributing to these emissions. That's what we found. Further on the right-hand side, you would see we have classified the organic aerosol sources into fossil, non-fossil. So the left-hand side, hydrocarbon-like OA represents the vehicular emissions. Then at the primary level, we had two more sources, which one was, so these names are based on which season they are emitted, or they are primary or secondary, and if we know the source, then we also put the name of the source there. And the other, so here we had the cold season primary OA, which represent that the concentration was higher only during the colder period. And then the biomass burning aerosol, these three were at the primary level, and then when they are oxidized. So here comes an interesting thing, that it is not very easy to identify that from where the secondary aerosols are coming. Generally, in source apportionment studies, you will see that we just say that 40% of it is secondary. But to identify the source, it is very important, so that then only we can take the effective measures, that whichever is contributing to the secondaries more and primary more, we control them. So here what we found further, so using the mass spectrometric techniques, we further analyzed, deep dived into the molecular level, and we found that the hydrocarbon, the vehicular emissions are also getting oxidized, and they are contributing to the factor which is urban oxygenated organic aerosol. And these cold season primary organic aerosol and biomass burning, they are also getting oxidized, and then we call these oxidized ones as cold season oxygenated organic aerosols. So that was a very important finding we had. And so here, bear with me for some chemistry part. So here, I'm showing you the molecular fingerprints of the primary organic aerosol. How did we identify these sources? So first one is the biomass burning organic aerosol, so which is basically coming from the wood burning, and the marker for the wood burning is levoglucosan, which comes from the pyrolysis of the cellulose, sorry. And so that was the only peak we had in this factor. Then we had the cold primary organic aerosol. So here we can find that after providing the molecular formula to all these species, we classified them into three categories: CHO, carbon, hydrogen, and oxygen containing compounds; carbon, hydrogen, oxygen, and nitrogen containing compounds; and then further with the more nitrogen. So this was an interesting factor. Okay, this was an interesting factor. What we found here that it was having two nitrogen atoms, and it was mainly related to the cow dung. So in the previous study, this factor was, these species were already identified in the cow dung and the brushwood burning. So the same species we have already also identified here, and they were ranging from C7 to C12 species, carbon number going from C7 to C12. And most of them were the imidazoles or their derivatives. So they are specific markers to the burning, combustion activities. It can be coming from the wood or brushwood or cow dung, but the specific ones we have identified here were coming from the cow dung. Then coming to the secondary organic aerosols fingerprints, here we can see the cold season oxygenated organic aerosol. So here also you can see the contrasting difference between the cold and the urban. So the carbon number is shifted to the higher side, and in the cold one we have the lower number of carbon atoms. And these carbon atoms, so we, after looking deep into the chemical composition, what we found that this was, the cold season oxygenated organic aerosol was mainly the oxidized form of the biomass smoke in the presence of the high NOx concentrations. And the urban oxygenated organic aerosol was mostly from the when the traffic emissions are oxidized, and also somewhat mix of the cooking aerosols. How did we identify that? So you can see at the bottom, in the first one, we found that the C4 to C7 nitroaromatics and furans were there. So here on the right-hand side, you can see in the middle one, you can see the species which are C4 till C7, and they have the nitrogen as well as the oxygen content. And then some of the oxidized species, which are also the markers for the oxidized species, were the C4 to C8 organic acids, which also come from the oxidation of these furans and nitroaromatics. Further, for the urban oxygenated organic aerosol, how did we identify whether it's coming from vehicular or from the cooking emission, or whether it was coming from some other type of combustion? So from vehicular emissions, we found that generally we have the long chain of alkane compounds, so C12 to C18 with the 3 to 5 oxygen atoms, and also some oxidation products of the toluene, TMB toluene, which we generally find in the fossil, in the fuel, and naphthalene. And for cooking, we had the higher carbon number fatty acids coming in the spectrum. Then we wanted to, as I said, that we wanted to look into that whether this is happening at a regional scale or at a local scale. So here you can see the last factor, which is the traffic factor, HOA factor. It doesn't have any seasonal variation. And if you see the concentration of it along different sites, you see that in Delhi it is more, which is more of an urban area, and along the upwind and the downwind it is less. And it didn't have any seasonal pattern, means the traffic doesn't change with the season. So that's what we found. And compared to it, its oxygenated factor had some of the pattern according to the photochemical activity that increases, sun intensity increases during the summer season. So that's why the concentration increased, and it also had a seasonal pattern. Then in contrast to these, so we identified one source. We have primary traffic and its oxidized one factor. And then the other one was the primary biomass burning and, and also its oxidized factor, which was basically the biofuel. So we can, one was cow dung, other was wood. And we also saw some impact of agriculture burning in these factors, oxidized ones, but that was very less. Since the period was from January to May, and we have this agriculture field residue burning
sorry to
period.
interrupt. Can we wrap up in another 2 minutes?
Yes.
Yeah.
Yeah, sorry. Okay. So we saw it during the April period, but it was very less. So overall, what we have concluded from here, that the OA emissions and the secondary formation is happening at a local scale, so that blame game we could not see during this period. So like Delhi blaming Punjab and Haryana for the agricultural residue burning and impacting Delhi was not there. But just bear with me, this is only half of the study. So we have also extended it to full year, and we saw that there is around 30 to 40 micrograms coming from the agricultural residue burning during the October-November period. So it is there, but not all the time. So both the local and the regional efforts needs to be taken to actually solve the problem. Then this is the last slide. So here, the main thing what we wanted to see is that which are the drivers of the PM mass as well as the oxidative potential. So here, the first thing you can see, the yellow one is for the PM 2.5, and the other blue shades are for the different acellular assays which we have used. So inorganics, although they make 30 to 40% of the total mass, they are not responsive to the oxidative potential. Then they are not contributing to the oxidative potential. Then the other factors, the primary as well as the secondary, which were coming from the incomplete combustion of both fossil and the non-fossil fuel, they are always contributing to the oxidative potential. So they are the main drivers of PM 2.5 toxicity in the northern India. That's what we have concluded, and it includes both biomass combustion as well as traffic, because it's fossil is also included. And when we compared the toxicity of the PM 2.5 mass, or the oxidative potential of PM 2.5 mass across the countries, then what we find, India sits at the top, and some of the Chinese city was also there competing with us. And then the European countries, they have a factor of 5 less, toxicity than our PM2.5. Also, it's a matter of the PM2.5 concentration, but how toxic is that concentration, that also really matters. So with this, I would like to conclude, and thank you. And for more details, you can have a look at the paper, which was recently published.
Thank you, Dr. Deepika. Can we have? Yeah. Thanks. So before we move on to the audience for the questions, I have a special questions to Anirban on we are having right now, we have published the city level EI. So, but we already have a global as well as regional EIs. So how does the city level emission inventory help us?
We have a couple of global level EIs, and most of them have published multiple papers also in that. So, but however, if you look at how they calculate the emissions, they take country level total consumption of fuel based on fuel type categories and disaggregate that based on different proxies. It may or may not be representative of the city you are taking up. Say, for example, if I go by there is something called National Family Health Survey. If you look at that, there is a state, district level information, and if you look at in that, it says that there is a stark difference between the LPG penetration or clean fuel penetration for cooking for southern India and northern India. Now what happens when you look at the total fuel consumption for a country level and disaggregate that, they may or may not look at those factors. And because of that, it may not always resemble what's the picture in the ground. When we are rather, also one of the factors is most of these global level EIs has a spatial resolution of 10 kilometer. So 100 square kilometer, you are getting one data point, which is many of our cities are barely 100 square kilometer. Bigger cities, yes. So let's talk about, if you talk Bangalore, you have 8 data points, and because it's 800 square kilometer approximately. Whereas if you look at our EI study, 1 square kilometer, you have 800 data points. Much more granular, much more variation is visible over the emissions, and to identify the hotspots and targeted interventions were also possible. Thank you.
Yeah, thank you, Anirban. Also, I would also like to know, it's an open question to everyone this panel, to identify, how do we identify the number of sampling sites required, or what is the procedure required for a source apportionment study in a city? If you have to do, what is the number of sites, and what are the challenges that we face when we have to identify this?
So see, basically, if you go through the CPCB guidelines, there are clear guidelines, like if that much population is there, then 5 sampling sites. If I think million plus, it's 7 sampling sites. So if you go for the pollution control board work, then you don't have much liberty to decide on that. But generally, what do we think is, according to the size of the city, we go for the signature sites like industrial, residential, curbside and all. And of course, like we decided for Jammu and now we are deciding for Srinagar. So the basic logistics and security of the samplers and continuous electricity supply and social acceptability, all of these things are very important in finalizing the sites. But yes, of course, about the number of sites, if you say, so if you are a researcher and you are planning a long-term study, then you can go for 3 sites also and 2 sites also. It depends upon the budget also. So, but city-wide, at least 3 sites and 5 sites, and if million plus, then 7 sites also the thing.
So, I mean, if it's a location where you don't have any yet, one is incredibly valuable,
Yeah.
right? And all this chemical analysis is expensive. And so I don't think you want to, I think you want to be aware of that it's a lot of work, and that, you know, if you need to say, well, we have to go from 0 to 7, that might deter a lot of people or groups.
Thank you.
One more point I would like to add, that we also look at the meteorology, because there might be some sources, you have to look at the wind direction from where it is coming. So it might be possible that while deciding the site, you leave out that particular direction and you focus only on the dense part of the, like where the population is living. So it's important that you look at that which will be the upwind and which will be the downwind, so that you have entire spectrum.
Yeah. Thank you. So now the questions are open to the audience. Yeah.
Thanks, Emil, and thanks to all the speakers for some really great, interesting talks. So one thing that comes to mind, I mean, obviously, both Shweta and Professor Bhatti talked about ACSM or AMS measurements, and these are pretty expensive equipment, right? Whereas Albert talked about, you know, maybe a low-cost analytical technique that still gives you time-resolved data. So a couple of questions. So is there like a way to get time-resolved organic carbon fractions from more conventional filtration? I think Professor Yadav mentioned lots of filter samples that are in storage, for example. Or I don't know what the technique is for oxidative potential, but is there a way to get more, you know, get analysis from all of these stored samples, ideally maybe in a more time-resolved fashion? So I guess to three of you on the panel. Thanks.
You will say first. Okay. Yeah. So I would like to say that definitely the filter samples can help, but co-located real-time instruments are really important, because when we have to look at the levels where, like I showed, that when you have highly oxidized species, that we will either lose the information because the tracers, they get lost. And until we use the molecular level information, we will not be able to identify, and it generally consists of, makes up 60 to 80% of the total mass. So other way, but real-time instrumentation is costly. We know that. It can cost up to 10 crores, a single instrument, and we cannot cover all the sites. So to complement that, basically the filter samples can be used, and also these mass spectrometers, actually in our field, they are not very popular, but if we go to bioscience departments or chemistry departments, they use these kind of mass spectrometers to get the deeper protein information. So we can always collaborate with them, get more information, and try to find out, like synthesize the information and find out the sources. So that would be my approach, to collect samples from different locations and bring it to the lab and do these kind of measurements. So.
Yeah, I basically agree, right? There are lots of methods out there that automate sample analysis, right? And especially if you have a backlog or a history of filters that you can do there's an auto sampler for an OCEC analyzer, right? You can extract them and do GC. And that, again, if there's one facility, then that one instrument that's expensive can process a lot of samples.
So I think I totally agree what you both have said. So only one thing to add is, like, this confusion always stays offline, online, and how to do it and how to resolve it. So if you talk about the collected filter samples which you already have, so our source apportionment project was little non-traditional in point of view to Pollution Control Board, because we came up with HURRY facility also, and we did diurnal sampling also, which generally source apportionment studies don't allow when done in collaboration with Pollution Control Board. But if we talk of time resolution or temporal scale, then how precise we can go? We collected 6 hourly samples, But we cannot compete with the ACSM measurements, of course. So there is a limitation like 24 hourly, 6 hourly, not less than that. I think with filter samples we can do. But yes, of course, that's what he was also making a point, that if there is no data, that is a valuable data. For any good start is good. Yeah, thank you.
Yeah, any question? Yeah, we have it back.
Yes, I have a question. The presenter on oxidative potentials, you have attributed all your materials or your compounds to be coming from biomass and vehicular emissions. I just wanted a clarification because most of these materials come from the burning of plastics. Did you encounter any burning of plastics in those areas that you sampled? Or maybe incineration? Thank you.
Yeah. So the waste incineration or burning of plastics, we didn't see any markers related to that, but there could be that their amount was too less, which might have lost into some factors or residuals. There is always a possibility. But closer towards our site, when we were also sampling the filters, we did not identify any of such activities. But if it was happening, it might have gone into the residuals, because that's the modeling constraint we have. If the concentration is too low, then it might not be identified very well.
Yeah, next question.
Hello, myself Vishal. I'm a PhD student from IIT Tirupati. My question is to Anirban. As you guys have developed emission inventory for so many cities, so as we use for the development of the same, so many different emission factors from different literatures and sources. So have you guys considered doing the uncertainty analysis for the same? If yes, then what is the range? Thank you.
In this project, we didn't look into uncertainties due to emission factors, because we only used CPCB approved emission factors, not others. And yes, for the PM 2.5, most of the industries doesn't have CPCB approved emission factor. So in that case, we looked into US EPA or EEA. However, to get back to your question, uncertainties due to emission factors were not looked into this project.
Okay, thank you.
Hello. Thank you for the presentations. Thank you for all the nice presentations. So I was looking at the NCAP target. So it still aims to achieve the reduction of PM10 by 30 to 40%. But the particles like from 2.5 to 10 mostly stuck in head airways and do not go into the internal part of lungs. So why not exclude PM10 and entirely focus on PM1 and 2.5 and source apportionment related to it and calculating oxidative potential related to it? And what are your views on that? Because it will save time too, entirely focusing on 1 and 2.5 would more help.
Very well said. So basically, see what happened initially, that we were having PM10 and PM2.5 data from pollution control boards. We were having more of PM10 data. So that's why PM10 data was used to identify the non-attainment cities. And that's why CPCB said that do the source apportionment of PM10. This is where we started with. But now gradually we said that PM2.5 is also important. Then they said, okay, you do source apportionment for both PM10 and PM2.5. So what you are saying is very well taken, really good thing. But to go to the ministry and get those papers changed is a task. So it is better to do at our levels the additional studies and complement the studies. Meanwhile, all these suggestions have been gone to the NCAP Secretariat and also to the boards and everything. So I think with time they'll resolve something on that and it'll come in black and white. Till then we all should work toward the targets. Thank you.
Yeah, so I think the remaining questions we can take up during the lunchtime. Okay, you have one more question, okay, please.
Yeah, unfortunately, I think we don't have standards for PM1.
Sorry, what's your question?
I just answered your question, I continued your question. answer. I'm telling that there is no standards for monitoring PM1.
Yeah, PM1 is far off. We are still fighting for PM 2.5.
Okay. So thank you all. Thank you.